Okay, let's start. First, the brief introduction to the Odnoklassniki. OK.ru is one of the most popular social networks, not only in Russia. Here you can see our top 10 countries by audience. Numbers here show monthly active users in each country. There's a lot of functionality expected.
Yeah, I just, if you connect here, then sound comes in back and...
Sorry?
Oh, sorry, I supposed to be quiet. Sorry, I tried to answer in a kitchen and it made mess. I'm sorry, I will just not talk now while you talk.
Okay. There's a lot of functionality expected nowadays from social network. So from the engineering perspective, OK.ru consists of 9,000 hardware machines running more than 20,000 tasks. These tasks are running either directly on hardware or in containers in our 5 private clouds. These tasks provide more than 500 unique performant microservices. And now we'll try to build one of these services together, a messenger or chat service. So in a typical messenger, a user could have a list of conversations or chats. An average user actively participates only in a limited subset of these conversations. Our stats show that only 5% of conversations generate 95% of requests to the service. Most of what data messengers store are, well, messages. In most cases, only up to 13 of freshest messages are seen and so being requested from messages data store. But these don't apply when getting the freshest message of each conversation to render it next to chat name here. These messages are unlikely to be requested for a second time. When rendering a web UI, a freshest message is retrieved for each conversation shown to user. For mobile UIs, for all conversations stored on a user's device. Let's aim to store at least 500 billion messages in, say, 5 billion conversations. This would take about 100 terabytes of data, and this is not counting a replication. This new service should be fast enough to handle more than 100,000 reads and 8,000 writes per second. Every modern messenger should have full text search function, so when some search text is entered here, we'll find conversations and messages containing it. And this means that messages should be reiterated to build a search index. Messages have not only text. Here we can see some simplified message table with the conversation ID here, ID of message within conversation, the author of message, the message type, finally the text of the message, and the list of file or picture attachments to the message. So messages in our service can be represented with the table like this one. And messenger service must implement the following operations. Get messages in the specified chat for the defined user. It can return different messages for different viewers because of the selective message deletion, appropriateness filters, and so on. That's why the viewer is among parameters to this method. Most of requests to the messenger service come to this method, so it should work as fast as possible. Get last messages gets a single last message for the supplied list of chats to render the freshest message for each chat in the conversation list. This one is the most heavy operation on the service. Numerous chats should be traversed to get the last message of each one. Add operations. Add a new message to some conversations. Search is a full text search of in-user conversations. Index messages operation build an index for the search to use. Let's try to build this messenger service employing the modern microservices architecture, of course. So users using their mobile phones or web browsers, either directly or using some front-end servers, communicate with the messenger service. The messenger service runs application logic for the service. The application state or data is stored separately in the dedicated database store. And it is fault-tolerant and highly available, of course. To achieve this, a database could do some form of replication, so it's distributed, replicated, and so on. But let's leave it out of scope for a while for simplicity. That's it. Let's try to go live. and see how the most frequent operation, get messages, could be implemented. To get it done, the query like this should be executed by the database. The problem here is that this query should be executed 100,000 times per second by the database, which generates some load to the service. Well, scaling is what microservices are all about. Let's start more instances of the service. And now we see that instances of the service generate more requests to the database, and now the database is overloaded. What next? We could either scale the database or make use of the knowledge that only 5% of data are hit by the majority of requests. Let's cache some. And the database definitely have a cache we can configure. But it turns out that database cache is not effective enough. It caches a lot of unused rows. This is because of other operations of the service. The get last messages operation and the messages indexing process are reading not only 5% of actively used conversations, but all 100% of conversation. These operations are very rare comparing to the get messages, but because they touch all conversations, all of them hit the database cache, flooding it with all those 95% of rarely accessed and useless to cache data. The database cache is typically restricted by few generic algorithms like the least recently used LRU algorithm, for example, and typically cannot be adapted for application logic to control which data should be cached and which should never be. So, either we should throw much more memory to cache all these rarely accessed data in the database cache, or be able to implement an explicit cache management in application logic of the service, so only messages which should be cached are cached. Let's introduce the memcached service for this purpose. This takes load off the database. When the load increases, we can scale the memcaches independently from the service instances and the database. Thus, we came to the typical modern service architecture many of us are familiar with. So let's delve into costs hidden in it with more detail. So the first is the CPU cost of the marshalling and unmarshalling. This is the process of transforming the memory representation of an object to a data format suitable for storage or transmission. To make a single request to a memcache, the application logic marshals the request and its parameters, and the memcache unmarshals this request to its own in-memory representation. After the memcache processes the request, it marshals the response. The application then unmarshals it. These marshalling costs also apply on the application communicating with the database. Intuitively, we tend to think this cost is negligible. The right thing to do is to measure it for an exact system, of course, but in this talk, I'll use measurements and results published in the excellent paper named Fast Key Value Stores, an idea whose time has come and gone, from the group of researchers from Google and Stanford universities. Please read if you're interested in how these measurements was made. So the link to is down in the bottom of the slide. So according to these measurements, this cost could be up and more than 85% to CPU load and can add up to 27% to median latency of the system. The second is the cost of overreads and overwrites. These are costs of reading or writing more data from cache than it is necessary. If it stored last 13 messages in the memcache packed to a single blob for each conversation, to render this list with a single freshest message next to each conversation, we'd read a blob containing all 13 messages for each conversation, marshal it, transfer to application, and marshal it to individual 13 messages, and throw away 12 of them except the freshest one. In this, the same paper states that if only 10% of data is used from all the retrieved data, like we have here approximately, we can expect up to 46% of CPU and 86% of network traffic wasted by overreads. The third is the cost of the network-related latency. Each request-response pair to both the memcache and the database introduce the round-trip time latency, or RTT. The additional delay adds up for moving the data over the network to or from the memcache, and the database can vary a lot depending on the size of the response. But the worst thing is that these latencies are multiplied by the number of network requests the application logic makes to serve a single user's request. For the get last messages request, a separate request for messages of each conversation must be made to memcache, making tens or even hundreds of requests. Well, as we can see, costs are high, but how can we lower them? Most of the load naturally fall into the memcache and it's linked to the application logic. So these costs are much more visible here, and most efforts in industry are spent on optimization of memcaches and their link to application logic. For instance, Redis and Tarantul are trying to fight overreads by introducing data structure in the memcache, allowing application developers to request only the necessary subset of data. Netcache fights network latencies by introducing the network caching embedded to the network switch infrastructure. KV Direct is about to lower CPU costs by placing unmarshalling onto the network interface card processor. We'll try to optimize the same thing from the different angle. These costs are introduced by sole remote location of the application state, so we can get rid of them by moving the state closer to the application logic. This way we come to the idea of stateful microservices. A stateful microservice combines the application logic with a custom in-memory store in the memory of the same single process. And so the network latency costs are not applicable here anymore. This in-memory store is custom. It has the application-specific logic implementation. This allows an application developer to implement a service application logic without overreads. CPU costs of unmarshalling could be eliminated or lowered significantly, selecting the appropriate application-specific data format for both components. Embedding distributed persisting store code to the same process eliminates same costs on the second leg of the architecture and allows us to easily integrate all components. Words embedded and distributed next to each other could be a bit mind-blowing. But what I mean here is that we embed the code of the distributed store. So this code runs within the same process. An instance of stateful service then becomes a normal node of distributed store, participates in distributed node cluster, stores data on a local machine's persistent store, and does all the necessary operations just like a dedicated distributed node could do. This way, we've got a more efficient stateful microservice. And it always is more efficient than the same application implemented as a stateless microservice because it has no more costs to pay for the external location of the application state. Let's also see how this statefulness affects the fault tolerance of the service. For this, let's consider what distinct failure scenarios could be in the simple distributed system of two communicating participants, the client and the server. The client sends a request message, the server processes the request and sends the response message back. So, what can happen? The client can send the requests and disappear from the network. The server can disappear as well. They can crash or reboot, or their hardware can fail and hang. A request or a response message could be lost. The network is failing, buffer underflow, or on either communicating party. The server could time out. A response is sent beyond the defined time bounds. The invalid value response. The server responds with a message the client can't understand. How could this happen? Easily. The server is running fresher version of the software, but client runs obsolete one. And finally, the arbitrary or Byzantine failure. A party makes arbitrary messages at an arbitrary time. This could be some bad intention actions like DDoS attacks. It could be bugs in code and so on. I discussed these scenarios in more detail in my talk Distributed Systems at OK.ru. Here goes the link in the footer to this talk. A total of 7 failure scenarios is possible. Let's try to apply them to both stateless and stateful architectures. Let's take a look at the stateless errors first. A user sends a request message to the application service, and the service processes it, sending requests and getting responses from both the memcache and the database over the network. So here we have pairs of simplest distributed systems. The first one consisting of the microservice and the memcache, and the second one, the microservice and the remote database store. What makes things worse is that failures to the memcache and the database are not unrelated to each other. So we must consider how a failure to the memcache will affect the part of operations working with the database, and other way around, how a failure of the database affects data in the memcache. So these failures are bound to each other and must be explicitly addressed by the application developer. So we have 7 failure scenarios here, another 7 to address on the database, and we have third simplest distributed system here between a user and the microservice itself, with yet another 7 failure scenarios to address. All of these failures are bound to each other, so an application developer must address all of them, plus their combinations when a failure in one component affects operations or state of another. This adds some complexity to the code, making such failure handling hard to implement in demand. Let's now take a look at the stateful architecture. There are same 3 machines, but their layout would be different. The sharding scheme would be different as well. For the stateless architecture, each of 3 machines are responsible for some set of keys K. When going stateful, each of the machines is responsible only for 1/3 subset of the original key set, each for its distinct subset. A user communicates directly to each stateful service instance, making the same 3 pairs of communicating parties. On each of them, the same 7 failure scenarios are possible. The only difference is that these scenarios are unbound to each other and not unique, because all 3 instances are implemented as identical components. So addressing failure scenarios here is easier. Such failure handling can be implemented uniformly for one pair and will work the same way for all others. To further evaluate reliability, let's compare probabilities of the full downtime. For stateless servers, downtime of any component, the memcache, the database, or service itself, leads to inaccessibility of all keys. So the probability of the service, downtime for keys from a set K can be calculated like this. For the stateful service, downtime of a single machine leads to inaccessibility only of a 1/3 of keys. Only when all 3 machines go down, each one with its own 1/3 of key, there will be inaccessibility of the full set of keys. So the downtime probability for the full set could be calculated like this. Which one is better is not obvious looking at these formulas, so let's try to evaluate these numbers. Let's assume probability of a single machine downtime to 1/10. This is very high probability, of course. In real life, they are much, much smaller than 1. But let's take this number for simplicity. Then we have these numbers for downtime probabilities. The smaller number is the better. We see that downtime probability of the stateful microservice is orders of magnitude smaller. In real life, people use replication to reduce downtime. So let's set up replicas for each component on the left. Installing the second replica reduces downtime probability of a component by an order of magnitude. Now we have allocated 6 machines for the stateless service. Is this setup more reliable than 3 machines on the right? Let's do our calculations with new numbers. Actually, no. Failures are still bound to each other, so both replicas failures still lead to downtime of the full key set. Let's try with 3 replicas on each component. A total of 9 machines against the same 3 on the right. Nope. The same replication idea could be applied to stateful service as well, and this makes downtime probability of 1/3 of keys smaller by an order of magnitude 2, and downtime probability of full set of keys by 3 orders of magnitude. So as we can see, the stateful microservice is more reliable. Okay, now let's get to the implementation of this idea. So what to start from? We want our service implementation to be highly available, so replication must be supported and consistency guarantees between the replicas must be defined. And we want our service to be scalable, so when load to our service increase, we could scale it by adding more instances. Now our application and its state are collocated, so it must implement resharding of the state's data among newly added instances. All this could be implemented, of course, by ourselves, but it's better not to implement this from scratch. These parts are really hard to get right. Instead, let's find something ready to use. All these words, replication, consistency guarantees, and resharding give us a hint to seek this in modern distributed databases. So first of all, let's decide which one's code we would embed. This database must be implemented in the programming language of the application logic to make code reuse simpler, avoid marshalling costs, and simplify an integration of components. It also must be open source, so necessary extensions of a database functionality could be implemented. OK.ru mostly used Java for our applications. We had successful experience running Cassandra database, so we choose it as a database for embedding. The first step to embedding the Cassandra is launching it in the same JVM together with our application. Looking at its startup scripts, we could easily find the Cassandra daemon class. It manages lifecycle of the node. So all we have to do is include necessary libraries to the class of our application and start the Cassandra node by this code. Cassandra.yaml here is a Cassandra standard configuration file. That's it. Now we have the database node running in the same process. When started, it will read its configuration from file and join the Cassandra cluster just like it was started by standard startup scripts of Cassandra. So as now we have state allocated with application, let's look how it changes the client request routing. So here we have our user, his name is Luke, and he is about to participate in the conversation. Which key falls into some set B. Luke uses some front-end system for this. That's why I rounded him with the green rectangle. For the stateless service, there is no difference to which available instance to send a request to. The front-end could make a request to this instance or to these instances. For all these instances, cost of sharing a request of a key from the set B is equal. Some network requests must be done to remote memcaches and databases to get the necessary applications. Contrary to stateful services, every instance has some part of keys stored locally. Leftmost instance owns some set of keys A, second owns B, and the rightmost owns C. This way, the instance owning the set B does not have to make a network requests for the data. It is either in the memory of the instance B process, or it can be read from its disks. Other instances can't access B's data locally and have to make network requests for it. The cost of processing B requests are higher because now should include costs associated with the marshalling and network latency. So To make the processing effective, clients must route their requests directly to the instance owning necessary data and avoid routing their requests elsewhere. This is possible if clients are aware of the cluster topology. I mean information about states, data partitioning across cluster nodes. Such client routing could be implemented on the front-end system in the form of a library. This library routes requests directly to nodes owning appropriate data partitions. So these nodes can process requests accessing the local data only. Data partitioning is the sole responsibility of a database, and we have Cassandra code just embedded. Let's take a look how Cassandra partitions its data. Every row in Cassandra has a primary key composed of two components. The partition key is used to determine the node owning the data. The clustering key is used to define the order of rows within a single partition and has nothing to do with data partition. Rows with non-matching partition keys fall into different partitions and could be owned by different nodes potentially. Rows with non-matching only clustering keys are in the same partition and will be placed to the same node ever. As in the messenger application, order of messages within single conversation is important, but order of different conversations between each other is not. We select the conversation ID as a partition key and the message ID as a clustering key. There are following components in the Cassandra code responsible for the data partitioning. The partitioner, given a partition key, calculates its token, usually applying some hash function to it. All possible token values are usually depicted as a ring. The partitioner is defined for the cluster once and can be changed in future. The whole ring is then split by token ranges. Mapping of ranges to primary nodes is stored in the token metadata. And the final component is the replication strategy. It defines how to select nodes for secondary replicas of data and how many of them should be at all. Different replication strategies could be configured for different tables. That's it. This information is enough to get mapping of all data to cluster nodes by this simple code snippet. The endpoint map here is exactly this. It maps max token range value to all replica node addresses. Transferring this map to the client, the partition-aware routing can be easily implemented then. Also to consider is that topology is not constant and can change over the cluster lifetime. Some new nodes join the cluster, some old nodes leave. So this map refresh should be implemented in clients as well as dealing with clients with the not yet refreshed stale mapping information. Here are various strategies we could use based on what suits the system most. Well, clients now route their requests for data to the right nodes. Let's look into how these nodes work with their data. So messages are stored in kind of this table, and we are about to implement get messages to get list of messages within a conversation. So it should execute a query like this one. To execute this query using data stacks Cassandra client drivers, we can use a code like this. You can find this code in the Getting Started manual on their GitHub page. So in the first line, a connection to database cluster is established. The second line sends a query over the network and retrieves a result set. In the third line, data is used. And connection to the database cluster closed. This is hidden in the final part of the try with this also statement. In real life, this could be even more complicated. Management of connections, their configurations should be retrieved from somewhere, some connection failure handling should be placed, and so on. To execute the same query on the embedded Cassandra, we call this class execute method. It executes a query with specified consistency level, binding specified values to query parameters and returns a result set. Please note that this method is static. There are no connection information, no any cluster configuration passed in parameters. That's because an application code is working in context of a database it has embedded. No database to connect to. This instance is the database. Accordingly, messages for our getMessages implementation could be retrieved from the embedded database by this code. To add a message, a query like this should be executed, and this code is even a bit simpler than we could write using the original database library. Looking at the query partitioner further, one could find even faster ways of executing queries to an embedded Cassandra. It probably would not be so simple to show it on this slide, of course, but even this simple and slow code will be faster and more effective than query execution using the original client driver. Okay, let's move to the implementation of custom in-memory message store. Let's start this approximating the volume of data it should store. The total amount of data is about these numbers. Only 5% of conversations are active, and only 13 messages of every such conversation should be stored in memory. Okay, now we have all data and can calculate what that's a fair amount of them should reside in memory. These numbers should be further divided by a number of nodes in cluster and multiplied to a replication factor. Let's recall the list of all requests the messenger service should implement. Only first 3 methods work with active conversations. So the new in-memory store should implement only these 3. Others touch non-active data and can flood memory with the relevant roles, as we discussed earlier. Let's implement getMessages first. A user named Leia opens the messenger and selects the conversation with Luke. I mean, the front end sends a getMessages request to the last messages in this conversation. The application logic looks for cached conversation in memory. Well, it's not there yet. Request messages from embedded database, places retrieved messages to the in-memory store, and returns them back to the front end. Feeling some disturbance in the force, Luke opens the messenger too and uses his Jedi powers to route his getMessages request to another yellow replica. The processing of the yellow replica is roughly the same. Messages are requested from the database, placed to in-memory store, and returned back to Luke. Caring about Luke, Leia asks him to go for a lunch. That means we have the add request arrived to the blue replica. Application inserts this new message to the embedded database and puts it to the in-memory store. The state of in-memory stored conversation is now like this. All done, the message is sent. Luke gets push on his phone, requests the first messages from a yellow replica. The application takes in-memory state of conversation, and Luke gets a stale state. No lunch. The galaxy is a green danger now. This is where the data freshness plays an important role. Adding the new message, blue replicas should somehow notify other replicas about it, so they can refresh their in-memory state. We could use the cluster topology information like we did before for client routing, determine all replicas which should possibly own this conversation, and notify them about the new message by sending a special edit request. Then the application would place a new message to the local replicas in memory store. It is not stale anymore, and the galaxy is safe now, but it is not. The problem is that this edit request is being sent from one replica to others over the network. So all 7 failure scenarios start to apply here. So this edit request could be delivered only to some part of replicas. The other part could not have it delivered for a long time, depending on what happened to the particular replica. It could simply crash due to hardware failure for a long time. Let's take a look how Cassandra is about to handle the same situation. Executing the sunset statement, it determines all updating conversational replica nodes, builds an update request, the mutation in Cassandra terminology, and tries to send it to all replicas over the network. because the messenger application and the Cassandra database node share the same process, this mutation message can be delivered to all replicas due to the same failure reasons. In this case, Cassandra stores undelivered messages to the local persistent store. Whenever the yellow node is back online, all the stored mutations are sent to it. This is called hinting. Usually these hints are stored only for a limited amount of downtime. Otherwise, healthy nodes could run out of disk space, storing all to be delivered hints for a single node's prolonged that due to single nodes prolonged downtime. So there are other ways of restoring a consistency between replicas. They include the re-repair, a process of comparing results returned by several replicas on the same query. If there are any inconsistencies detected, a mutation message is sent to the stale replica. And the final way is the streaming repair, a background batch process of iterating and comparing through data stored on all replicas, where then mismatched ranges of data are exchanged between nodes. Because the volume to exchange could be large, new data are exchanged in a form of the SS table file over the separate streaming connections instead of sending individual mutation messages. These consistency support methods are hard to implement and debug, so it could be wise to not re-implement them all for the in-memory store. So what could be much easier is on receiving the fresh data by the database engine by either normal mutation, hint, read, repair, or streaming, the database code could notify the application logic, which then refreshes the in-memory state to include the fresh data. I mean, we define this application apply mutation listener interface in the database engine code, implement it in the application code, and have it called back by Cassandra. This functionality is not implemented in stock Cassandra currently, so we have to extend it by ourselves. Luckily, there are only two components to extend. All mutation messages, regardless of its source, normal, hint, or read repair, come from this method. The mutation parameter here is the mutation data with the first data for several tables. We can take data from here and pass it to the listener. On completion of whatever is a stable streaming, this on completion runnable is run. We could take stables from the collection, iterate over them, reading from it, and send fresh data to the listener. Consider now the same case. The mutation message can be delivered, but not due to network failure, but because the yellow replica server is crashed and gone to reboot its operating system. Its in-memory state is vanished. Now hints can't help. Hints contain only fresh data were seen by a rebooted node, but get messages needs all data lost from the in-memory store and the fresh one. We could get the vanished data by retrieving it from the database. This retrieval should be performed for every conversation which was active before the replica rebooted. This should lead to the massive spike in amount of read queries right after the node is started. And because reads are served by a quorum of nodes in Cassandra, some network communication occurs for every read. There is a strong chance of catching the cascading failure of the whole cluster due to this spike. How to fix it? Well, one could use the well-known strategy of having a periodic in-memory state snapshot to a persistent store combined with write-ahead log of changes between two consecutive snapshots. But again, thanks to the embedded database code, we could avoid re-implementing this from scratch. We create the caches T space with the local replication strategy. This strategy basically instructs Cassandra not to replicate data on cluster and store it only locally. Then we declare the messages snapshot table there, and whenever data is put to the in-memory store, it's being written to this table. If data is evicted from the in-memory store, it's being deleted from this table. So this table now stores the copy of in-memory state. On node start, it loads the state by executing this simple select query. This loads a lost state from a persistent local storage, and hints apply the fresh data a bit later. This select query works fairly fast because it iterates sequentially over locally stored data, but still it takes some time, and this waiting time should be avoided when restarting a node normally due to application new version deployment or maintenance. Loading state on persistent storage can be avoided by using the shared memory to store the in-memory state. A shared memory is not cleared on the application restart until the machine is not rebooted. The simplest way to employ the shared memory is to open this file. It is better to use a memory mapped file, of course. For Java, ready-to-use structure could be used. They are implemented in our OneNeo open source library. Shared memory map and its subclasses provide the necessary functionality. In Linux, the TMPFS file system usually is mounted on the dev SHM path. It's fine. We also use huge TLBFS file system with larger 2 MB pages. This allows to lower the number of TLD misses accessing the shared memory and can conserve a bit of CPU cycles in heavy loaded cases. This makes things much faster. Starting the node with the shared memory map, only a quick sanity check is performed on startup now. The start became so fast that part of the requests hit just started replica before other replicas sent all pending hints to it. And Luke could get stale data from the memory store again. This is because the hints delivery is asynchronous in Cassandra by design. Cassandra reads data from several quorum replicas every time, comparing results returned from every replica to others. So it can detect and throw away stale data before returning them to client. This heavy read makes the hinting an optional optimization, which is not strictly necessary for the consistency. The messenger application gets 15 times more read requests than writes, so it is better not to use such a heavy reads for its consistency resolution. So right after initializing the in-memory state locally, we start the embedding Cassandra cluster services and waiting for hints to be delivered from healthy nodes. Only after all hints are played, the application is allowed to start to accept requests. This waiting looks like some kind of distributed coordination. We tried several strategies, and now we made use of the simplest one. The starting node periodically resends a check for unplayed hints requests to other nodes. It waits then until all nodes confirm they have no more hints to play, and then suggests it is itself in consistent state. So that's all about the in-memory stores in today's talk. Let's have some summary on them. In Stateful Microservices, the in-memory store shares the same process with the application and the database node. It is custom, and application logic is implemented on it. Application objects are stored and manipulated in memory of the application service. This allows to avoid unnecessary costs associated with dedicated remote caches, marshalling and marshalling overreads, and now easily avoidable by careful application querying. Network costs are not applicable at all. The data freshness is the hard problem for remote caches to solve. We solved it by extending the embedded database engine code with mutation listeners. They allow us to add an application logic on a new or updating data, so we could guarantee and memory cached data is as fresh as it is in the database. The state loss problem should be addressed for any of memory store. We solve it by replaying in-memory updates to the local database table and use shared memory to avoid loading a multi-gigabyte state from a persistent store on every normal restart. In stateful services, in-memory caches could have the same consistency guarantee as the database. And this is very hard to achieve for remote caches. Now, let's see how effective the implementation of get last messages request processing could be. This request retrieves a single freshest message for a list of users' conversations. To handle this request, a list of messages has to be retrieved for many conversations. Different conversation could be owned by different application service instances. There are no single instance owning all data. These message lists should be retrieved mostly from inactive conversations. As we can see here on this screenshot, only one from many of the conversations is selected and active. And this means that these conversations are absent from the in-memory store, and there is no point to log them there. Inactive conversations remain so most of the time. Messages of inactive chats are highly likely consistent across replicas. Most of the consistency procedures, hints, and repairs had their chance to run. Whenever inactive conversation becomes active again, it would be loaded into the in-memory store. Probably we could make some optimizations based on this knowledge. We'll see. For stateless service architecture, we would have it implemented this way. The client sends GetLab messages in the microservice, and then it would retrieve message lists from mem caches for every active conversation, and then from the persistent database shards for inactive ones. Contrary, in stateful services, there is no single instance to call. Any single instance is required to make a network request for all data not owned by it locally. And this implies costs we are trying to avoid. The effective way is to have GetLast messages implemented on all participants here. Microservices have their own implementation, and client has its own. Client's implementation uses the service cluster topology information and splits list of conversation IDs to several sublists. Each sublist contains only IDs of conversations owned by a single service node. Then it selects the replica for the first sublist and requests last messages from it. The same happens for the rest of sublists. Service instances process these requests, each for its own subset of conversations, and return only a part of response to a client. A client waits for all necessary partial responses from services, collects and merges them into a full response. It is essential to call all necessary replicas in parallel to keep duration of the request processing shorter. We also do here a speculative requests to several replicas for the same subset of the keys to avoid sudden single replica slowness to influence the whole request processing time. This is called speculative retries, and you can find more on this in my distributed talk. On the server side, GetLast messages also has some interesting topics to discuss. Let's start this implementation with the straightforward way. First, the in-memory store is called to retrieve the last messages of active conversations. Then the embedded database code is called to get freshest messages of inactive chats. But Cassandra is distributed database, and this means that it makes numerous network requests for data from several replicas to build a consistent response. But we know that data consistency is not that important for inactive conversations. Replicas are highly likely own consistent data for them. So we could skip this consistency resolution and additional network communications, retrieving only a local copy of replica's own data. There are no standard way to skip the replica consistency resolution using database client drivers. But on embedded Cassandra code, we could call not only public API methods, so we could call local reads using this code. Here you can see a lot of some magic, but this is all basically prepares a query statement, means statement parameters. The main difference is here, the execute locally is called. This allows to skip costs of network communications setup and execution. Now we have to implement the last function for today's talk, the full text search. Whenever a user enters some text in the search field, all messages across all these user conversations should be searched and shown in the conversations list view. Of course, scanning for text through all messages of all conversations is not feasible. Even if local reads are employed, a total data set of the messenger is over 100 terabytes, so even 1,000 machines cluster cannot make it fast enough. So we have to build an inverted index using, for example, Apache Lucene. A single large inverted index containing all conversations would not work. This is another interesting topic to discuss, but we are running out of time. So you have to believe me here. A separate index per user would lead to unnecessary data duplication because many users participate in any single conversation. So we have to build an index per every conversation. This index contains only messages of a single conversation. We build indexes upfront only for large conversations. For short ones, index can be built right before searching. So let's start with a straightforward implementation. Whenever user adds a new message, the Lucene index writer add document is called to index it. And then we call Lucene to commit index. And this would not work. Too often commits leads to too often merges of Lucene index segments. These merges are both CPU and disk expensive operations. Contrary, do not calling index writer commit leads to too many open indexes because a single service instance adds hundreds of messages every second to multiple conversations. This could eat too much memory. A good solution here would be some background process. This process would preliminary merge new messages of a single conversation into a single collection as soon as messages are arriving, but not too often to keep the size of these batches moderate. And Cassandra has such a background process named compaction. If you wish to know about this process in more details, here's the link to read in the footer. In short, compaction merges different generations of data flushed at different time to persistent storage. Compaction is necessary for Cassandra to keep its data structure optimized. Compaction iterates over data to merge always in order defined by row keys. A single conversation is iterated at a time. Messages of the single conversation are iterated in order of their IDs. Compaction is managed by the class named Compaction Manager. We could easily extend it to call some listener interface, which we implement in the application to call necessary Lucene indexing. And voila, now the stateful service can do the low overhead massive data processing. This processing could be used in many other cases when iterating over a full dataset is necessary by an application. This is the last crazy trick for today, but not the very last of all the possibilities. What I wanted to illustrate here is that embedding the database code allows for tighter integration of the application and the database, allows to extend the database in the ways necessary for the application, and allows for even more cost reduction across many aspects, not only related to requests processing. So we are now the last section of today's talk, the production operations of stateful services. From the operations perspective, stateful services also have their own particularities. Let's look into them. The first problem to discuss is longer deployments. This is because of the longer start time of the stateful service. This is because stateful service embeds the database. This database has to perform a persistent data initialization at startup. The installation time is mainly bound by speed of persistent storage, speed and volume of write-ahead logs to replay. Another thing to wait is the in-memory store loading the lost state from the messages snapshot table we discussed earlier. This time is bound by the size of the state to load, frequency of change and eviction events, the CPU power, the number of key collisions. This could last for minutes and tens of minutes. The consistency wait time, we should wait for hints to be replayed by other nodes. This time depends on number of skipped mutations. So if deployment process stops and starts instances one by one, the total deployment time is proportional to the total number of instances and could easily last for a day for several hundred instance deployments. So to mitigate this, the deployment process should not be sequential, but parallel, deploying multiple instances at once within a single availability zone. Our deployment process, for example, deploys a single instance first to make sure the new version is not broken, and the rest of instances of this availability zone deploy in parallel. Instances in the rest of availability zones deploy in parallel at once. This way, total deployment time remains constant regardless of the total instance count and depends on the availability zone count +1. The second problem is we restart database nodes more often. Well, we embedded the database to the application service node, so we restart the database node in each availability zone each time we have to deploy a new application version. Should we mitigate this? Actually, no. This is not a problem with today's fail-first database, like Cassandra. Moreover, these deployments actually test an availability zone outage on every deployment in the controlled environment and during the work hours. So bugs in an availability zone outage handling could be detected and fixed early, before the real outage occurs. The third problem is longer scale out. This is because data is collocated with the application. So to add new instances to the application, data should be resharded, I mean physically moved over the network to the newly added instance. This problem is not specifically unique to stateful services. Stateless services require resharding to scale out their database and memcache components too. Still, could avoid resharding for application logic originated CPU or network-bound loads. These urgent needs for the CPU or network consumption by application logic is often related to some new functionality. To mitigate this, a capacity planning should be in place. This longest time should be taken into consideration, so an application could be scaled out before the load spike hits. To mitigate load spikes rooted in the new application functionality, feature flags could be used for a new code, so they could be employed to cut off the problem code. There, of course, could be cases when application-sourced load spikes are unpredictable, externally rooted, and highly volatile. And the only solution is to have fast auto-scale, which implies no resharding is possible. And so these measures may not help, and sticking with stateless microservices architecture may be a better approach in these cases. The fourth problem is somewhat the development of the previous slide. This problem applies only to applications with consumption of one of the machine resources is much higher than others. To our experience, these cases are somewhat rare. Imagine a service which needs high amount of CPU to do complex calculations over some small amount of data. Such an application would consume all available CPU of the machine, leaving disks underutilized. It is impossible to install a fraction of disk into a machine, so the underutilized resources of the disk would be wasted. On the contrary, we could imagine an archived service doing very little processing over large volumes of data. Disks of this service would be full of data, but this machine's CPU would be idling. Stateless services allow each component to be scaled individually, so these imbalances could be mitigated by scaling out stateless service components more for the first application and scaling down the database more for the archived one. For stateful, this is not possible. State and application logic are collocated. These imbalances could be mitigated by employing containers and orchestration management systems. They aim to balance resource utilization across the fleet of the machines automatically, collocating different containers with different resource consumption properties, keeping distinct resources utilized evenly. A container with high CPU and low disk consumption would highly likely be collocated by orchestrator into the same machine with container having low CPU and high disk resource consumption. This would keep resources consumption of the hardware fleet leveled automatically across an organization. We use internally developed OneCloud orchestrator for this, but there are several of others available. Kubernetes is one of the popular nowadays, but there are others as well. On the bright side, the diagnostics and support of a stateful service are easier than stateless services because the application logic, the in-memory storage, and the DB share the same process. It is much easier to diagnose and debug. Setting a breakpoint in somewhere in application logic, one could easily track down the problem to the root of internals of the database and even down to OS kernel. Running the profile, one could track down performance problems more easily. Here you can see, for example, profiler run on stateful service showing flame graph of the CPU time spent from the application code here down to in-memory storage, stack traces, and database engine operations here, as well as down to kernel space here. By the way, this flame graph is built by Async Profiler, one of open source projects we originally developed within OK.io. It's low overhead, so we can run it safely on Java servers in production. For stateless services, memcache and database run on remote processes. Profiling and debugging an application often can't show the root problem. Running separate profilers on memcache and on a database can show the application context. Most of stack traces start somewhere on network dispatcher, hiding them may be the root of the problem, which is application specific. So diagnostics are often end up on custom database diagnostics tools or even random guesses if tools are inadequate or doesn't provide the necessary details. And we are now the final summary slide of my talk. Stateful microservices are more effective and reliable, and application logic shares its cache and database in the same process. There are no network between them, so avoiding bashing and network implied costs. The custom implementation of in-memory store avoids overhead costs. Stateful services have an in-memory state consistent with this database state, which is hardly achievable with remote caches. This is not so hard to implement, it having embedded modern distributed fail-first database. On Java, the OneNeo library could be used to build custom in-memory stores. Stateless microservices was invented more than a decade ago. Problems to which stateless was aimed for could be solved now in new ways. There was a lot of progress during the last years in distributed databases with seamless auto-sharing support and designed to be fail-first from ground up. Containers and orchestration systems are good at the process isolation, and the hardware-machine automatic utilization leveling allow us to avoid externalizing an application in memory and persistent states in remote systems and open a road to build more effective and reliable services. Thank you very much. Now I'm ready for the questions, so we go straight to the kitchen.
I think we go with questions at first, 5 minutes, and then to the kitchen.
Okay, any questions, guys? Not everyone lived through the whole presentation, I see.
I will delete previous questions, those who are an hour ago, but here are 2 fresh questions. Can you find them at the right side at Q&A?
Q&A, I see it. What local in-memory storage use messenger service? It is custom. It is built using the OneNeo library. It's OneNeo library. You can find it on GitHub. It's open source in Java only. If you know Java well, it aims. It targets on storing the data off heap in Java in the off heap memory of the Java process. Then some anonymous. Stateful way might help with reliability of the system, but in case all system components, service A, cache, and DB are scaled all together, then the resources not Not effectively optimized. This is, I believe you are talking about this slide, the imbalanced resource utilization. The answer is use the Kubernetes or Mesos or Aurora, or go work to Odnoklassniki and you'll have a chance to use one cloud. Again, orchestration systems make sure your hardware or your virtual machines are loaded evenly, even if different containers consume different resources differently. One container with high amount of CPU utilization will be collocated this in other container. Thus, the machine will be loaded uniformly across the whole fleet. You don't have to manually do it, because in stateless services, you will manually decide which component needs more instances and which needs less instances, to balance your hardware resources manually. Deciding it's manual labor, manual planning. In systems like Kubernetes, you can leave it to be leveled automatically by the algorithms, by the machine. And this is what we use a lot nowadays. I can give some numbers. We previously, like 5 years ago, we also manually planned the hardware utilization of the machines. The resulting numbers was about the efficiency was about the 10% of the hardware fleet machine was the utilization was about 10% of the capacity. Now, after the deploying the one cloud system, we have about 40% of utilization across the fleet of the machines. What is deployment frequency per day at OK? There is no such thing as deployment frequency, because all the system consists of about 500 distinct microservice clusters, and each of the development team decides on their deployment individually, so they deploy as they want. So it's kind of hundreds per day, I believe. But again, there is no procedure to roll out all changes of the Odnoklassniki in one shot, because the changes applied gradually to distinct microservices at a time by different teams in parallel, whatever. Does this architecture and Cassandra storage make maintainability more complex for developers for usual work with them? It makes its maintainability more simple for developers, because the developer is now responsible for his application, she's application in full. There is no such guy as DBA who does the kind of strange things to database, and you don't know what things they do. All the responsibility is on the developer, and developer can do necessary diagnosis to his application by himself, not asking anyone. So the maintainability is much more simpler for the stateful services. And this also promotes the knowledge to the application developers how the database works. So the application developers are aware, are becoming aware of the application or the application internals, and this allows them to more for a more to have more information to make smart decisions about the architecture and so on, because they see how this works in the profilers, in debuggers, and so on. What is deployment attack? Does data replication Cassandra consider to be reliable process for end user application? Of course, it has configurable number of replicas. You can start with 3 replicas because this is the quorum system. The downtime of a single replica passes unnoticeable by the application, and if you need more than one failed replica, then you can make 5 replicas, 7 replicas, whatever you want, number you want. How it's more about your SLA. It is much more reliable than the replication of your favorite classic database. Oracle, for example, makes only 2 replicas, and if the master fails, then you'll lose some transactions which were in flight. For Cassandra, this is impossible. So any instance of the Cassandra can go down, and you'll not lose data. What's the thing you would do differently now if you look back to the infrastructure that has been built? There are no what if question in history, and anyway, the infrastructure and decisions which are made now are based on the previous decisions and previously existed infrastructure. And as far as I know, we didn't made kind of critical mistakes. All this plus minus was good and is good now. What's your cloud choice? Do you use AWS, and what you think about it? If you are about the high load, don't use third-party clouds. Build your own infrastructure. This is my choice. Because in your own infrastructure, you can guarantee at least some things. For example, you can guarantee the round trip time in your network infrastructure. You can guarantee that the machine you use is the real hardware machine. This is not the case in the most public clouds. So if you tried to ping from one server to another, you'll notice that it is very unstable. In the normal hardware data center, ping time from one machine to another would be constant, and it would be fractions of milliseconds.